There's only a little bit of stuff left before the final. People have been asking me, what's going to happen? What if I get, B on here, and an A on here, and an F there, and whatever? What's my final grade going to look like? Okay? The final is designed to help your grade, not to hurt your grade. Final part 2. Okay? So if you take the final part 2 and you do well, it's going to make a big difference in your final grade. If you do badly, it's not going to make a big difference because, you have all the other stuff. It's not going to drag you down very much. But good grades in the final will help. Final is not really going to be harder, it's just going to be the material we haven't put on part 1. Related rates, implicit differentiation, maximum, minimum, graph, some of those word problems that you love so much. I saw a couple of eye rolls just then. And then the new stuff. So this week we're going to go through the final set of material. And next week I'm going to do a review on Monday and Wednesday for the final. And then we have a review session scheduled a week from Monday, May 11th, at, I forget what it is. I'll post it. I think it's 12 to 2. Okay? And it's in Javits, so you can bring your friends. You can bring your enemies. You can bring your dog. Actually, you can't bring your dog, Michelle. Okay? Everybody good? So we're going to do L'Hopital's rule and what's called Newton's method. I need to look something up for a second. One person bought the book. It's very exciting to buy the textbook. Most people don't. I didn't hear you. You use this book again for 126, but again, you don't need to buy it if you don't want to. Okay? I'm going to design a course. You do not need to buy the book, but you should feel free to buy the book. Come on, where is it? There it is. All right. So now we're going to learn L'Hopital's rule. L'Hopital. Okay, so L'Hopital was a French guy. He actually wrote the first calculus book in 17 whatever. It means the hospital. He's the hospital's rule. Okay? I don't know who the Marquis de L'Hopital was, but he was a rich guy who paid very smart people to do lots of research, and then he took their research and claimed it was his own, but he paid them for it, so it was okay. And he told them in advance. He said, I'm going to hire you to do research, and then if it comes out well, I'm going to put my name on it. And that's okay. That's what makes America great. Except he was French. So what is L'Hopital's rule? And by the way, you might find this very useful on part 1. Even though you technically don't need it, you may find it useful. L'Hopital's rule is a way to do limits for what are called indeterminate forms. So an indeterminate form is a limit where you end up with something like 0 over 0, infinity over infinity, a couple of other types. So we've seen some examples of that already. So L'Hopital's rule is another way to solve these. Okay? And it says, suppose the limit is x goes to a of f of x equals 0. And the limit is x goes to a g of x equals 0. And the limit, and some minor constraints here and there, of f of x over g of x okay, suppose the limit is x goes to a of f of x is 0, and the limit is x goes to a of g of x is 0, then the limit is x goes to a of f of x over g of x, which is going to give you 0 over 0, is the same as the limit, you can't really see this, of f prime of x over g prime of x. That's very handy. For example, suppose we want to do the limit as x goes to 1 natural log of x, also known as n of x, over x minus 1. Okay? So if you have log of x over x minus 1, oh, guys, I forgot. I need my baseball cap. Go this way. Is that backwards or is that forwards? This is forwards. This is backwards. What do we do? Well, you look at this, you say, but if I plug in 1, the log of 1 is 0. And if I plug in 1 in the bottom, I get 0. So 0 over 0, the limit does not exist. Wrong. The limit does exist. So what do? You take the derivative. Now, this isn't quotient rule. It's just the derivative of the top divided by the derivative of the bottom. Now you take the limit. And that gives you 1 on top, 1 on the bottom. So that's 1. It's not does not exist. It's not 0 over 0. It's just 1. Suppose we had I'm so popular. So this is already kind of violating my rule. You can also do this with infinities. So as well as where f of x goes to 0 and g of x goes to 0, they could both go to infinity, which would give you this form. You can do L'Hopital's rule again. So you have e to the x over x squared. This is the same as the limit as x goes to infinity of e to the x over 2x. And now when you plug in infinity, you get infinity over infinity. So what do you think we do? Do L'Hopital's rule again. You get the limit as x goes to infinity of e to the x over 2. Okay? Now, it's infinity, so we know the answer is infinity. Yes? Infinity over infinity wasn't 1 here, it was infinity. Infinity over infinity, it depends on the type of infinity. Okay? In other words, it depends on how fast the top is going to infinity versus how fast the bottom is going to infinity. They're both going there, but one is going so much faster than the other that it dominates the function, and it's as if the other function doesn't matter. Okay? All right, what if we had now you should be able to look at that and instantly tell me what the limit is, right? 3 over 5. But let's do L'Hopital's rule, because you've got infinity over infinity. So take the derivative, and you get 6x plus 6 over 10x minus 2. Once again, that's infinity over infinity. So you do it again. And now you get 6 over 10, which, oh my God, is 3/5. Awesome. Like, dude. Okay. I think it's that way, actually. Everybody have a good time at the concert on Friday? It was 21 Pirates, or whatever it was. Death at the Disco, or something like that. I thought they were pirates. I was all excited. I had my mask and my eye patch. And no, it didn't happen. All right, so that is one aspect of L'Hopital's rule. This could be handy, for example, if we had a trig function. I know, you're saying, why didn't you teach this to us earlier? Suppose we had something like that. And you plug in 0 and you get 0 over 0. That's bad. Because we don't know what to do with 0 over 0. So we do L'Hopital's rule. Mr. L'Hopital is very proud of his rule. Even though he didn't actually do it, it was one of the Bernoullis. We're just not sure which one. We have to do a little research to figure it out. As I said, it's like the Pythagorean theorem wasn't actually necessarily done by Pythagoras. I know, you're shocked. But he gets the credit anyway because, well, you know, there you go. Alright, what's the derivative of sine of 4x? Cosine of 4x times 4. And what's the derivative of sine of 5x? Cosine of 5x times 5. Now when you plug in 0, cosine of 0 is 1. Cosine of 0 is 1, so this is just 4 over 5. Okay? So L'Hopital's rule is very handy. I would make sure that I knew this rule for at least the next 2.5 weeks. After that, you should remember it for second semester, and then you can forget it, or not. Now there's other types of what they're called indeterminate forms. Suppose we had... Oh wait, does somebody have this written down? It's going to be on video, not... You don't really watch those videos, do you? No, okay. There you go. Madison watched it. Yeah. So you got the hat, or the hood. What's that? Okay. What do you do if instead of you have like infinity over infinity or 0 over 0, suppose the limit as x goes to something if f of x is infinity, g of x is infinity, what would you do with f of x minus g of x, which is infinity minus infinity? Infinity minus infinity should be either infinity or 0. That would kind of make sense, but not necessarily. Suppose you had to find... Wait, we'll erase for a second while you guys copy. Any ideas? What do we do? Well, that's always a good answer in calculus classes to take the derivative, but not quite yet. Well, we want to turn it into what we just did a minute ago with L'Hopital. So what could we do? Remember fraction? Remember the trig identities? Secant is the same as what? I know you memorized these and then forgot them. That's called not actually memorizing them. Right. And tangent is sine over cosine. You're going to need to know the unit circle next semester, too. I know. Tattoo. You come back with a tattoo, you get an A for the course. No problem. You should tattoo the unit circle here, too. It'd be very entertaining during the exam. Do that. Although the people sitting behind you will be very grateful. No mirrors. No mirrors, sorry. You're right, it's not a calculator. We'll think about it. First get the tattoo and then we'll talk. Alright. It'll be great if they screw it up. Alright. So now, we could turn this into 1 minus sine x over cosine x. Aha! Now, Monsieur L'Hopital will help us to solve the problem. Oh, I keep writing infinity. This isn't to infinity. I'm sorry. Whew. My bad. That's as x goes to pi over 2. It doesn't work with infinity. Yeah. Wow. One of those days. Okay. That should be x goes to pi over 2 from the left side, pi over 2 minus. So if you're thinking of the graph coming out of the origin, the first branch of the graph. All right, now we could take the derivative. And you would get minus cosine x over minus sine x. Okay, that's cotangent of x. Or you could just plug in the pi over 2s and see what happens. This gives you 0 over 1 equals 0. Okay? So, you had, when you plug in pi over 2, you get infinity minus infinity. Okay? You do a little rearranging, and you can turn it into a fraction. Now, when you do L'Hopital's rule, you get an answer. Lilo, you look confused. You okay? Got it? All right. So that's another fun example of L'Hopital's rule. What are some other ones that we thought we would test? Let's try a couple. Here's 3 to try. Have some fun with L'Hopital's rule for a couple minutes. I think enough people are waiting for me that I should move on. Are you ready? Yes? Wir sind fertig? Ja? Ja. Okay. So, limit as x goes to infinity of log of x over the square root of x. Well, let's see. Log of infinity is infinity. Square root of infinity is infinity, so we can't do much with that. We can take the derivative of the top and bottom. And we get the limit as x goes to infinity. The derivative of log of x is 1 over x. And the derivative of the square root of x is 1 over 2 root x. Okay? Now, we could take this. Right now, if we plug in infinity, we get 0 over 0. That's not helping. So, invert and multiply. Flip and multiply. And you get 1 over x times 2 root x over 1. Which simplifies to limit as x goes to infinity of 2 over square root of x. Now when we plug in infinity, we get 0. Okay? How are we doing that one? Good? Okay. You're going to win tonight. Okay. Second one. Let's take some derivatives. Limit as x goes to 0. Anybody see this? Am I still in the way? 0. Okay. What's the derivative of sine of 8x? Cosine of 8x times 8. Derivative of tangent of 4x is secant squared of 4x times 4. Okay. Now the fun part is when the sine of 0 was 0, that causes you a problem. But the cosine of 0 is 1, that does not cause you a problem. So, 8 times cosine of 0 is 8 times 1 is 8. 4 secant squared of 0. Well, cosine of 0 is 1, so secant of 0 is also 1. So that's 4. So this comes out 2. Did you get 2? We could have gotten 8 over 4. Weberstein might not have accepted that, but I will accept it. Alright. I'm going to give myself a little better room for this one. I have 1 plus 2x square root minus 1 minus 4x square root all over x. When I plug in 0, I get 1 minus 1 is 0 over 0. So now what do? I copy off my smart friend. Or I can use L'Hopital's rule. But why did I break this into 2 fractions first? I can do that. It just makes it easier to do all this stuff, right? I don't have to. Do you not want, yes? You want to rationalize it? Let's rationalize it. You want to do that? Let's see. How about, you think that's going to work? Why? Well, we're going to need L'Hopital's rule eventually because that's what we're doing right now. I know you guys can't hear what they're saying, but they don't have anything important to say. It's okay. It's just, audience chatter. What happens if we rationalize this? We'll get 1 plus 2x minus 1 minus 1 minus 4x. What did I do here? So let's see, we get 6x on top, and some x's cancel, so we get 6. How do I get that? 1 plus 2x minus 1 plus 4x is 6x, which cancels with that x. So I get, well, I'll leave it there for a moment. I get 6x over x times okay? So I still got 0 over 0. And now what happens? That should be a 2. Does that work? What do I get? X's cancel. And now I get 6 over 2 is 3. There you go. Didn't need L'Hopital's rule. You don't always need L'Hopital's rule. I just copied this problem from the book. I didn't check. It says use L'Hopital's rule if you need to use L'Hopital's rule. So here you didn't on this one. No, actually. The question was, did you need to use L'Hopital's rule on this one? The answer is no. Okay? You should have a bag of tricks. So when we give you limits on the final, Okay? You should try to do it without. You should try to do it with L'Hopital's rule. You should see what works out. Okay? I don't know if we're going to say use L'Hopital's rule in the exam or not. Haven't figured that out yet. That's because we haven't written the exam. All right, that's enough L'Hopital. Let's do the other thing. This is called Newton's method. Newton actually did Newton's method. Alright, hat goes back off. It's serious now. Alright, Newton's method is a method for finding roots of an equation. Suppose we know that we have some graph and there's a 0 right here. How could we find that 0? Well, you plug in your calculator. But if we didn't have that calculator, Newton came up with a very clever method. He said, we know it's here, so let's pick a value that's close, like here, and draw the tangent line. Okay? So you'd say, well, now you get an answer right around there. Now you draw the tangent line at this spot, and now you get an answer that's right around there. Then you draw the tangent line at that spot, and you get really close. So you use the answer each time to find a new answer. Let's do that again. Blow that up so you can see what's going on. I want to find the 0, which I know to be here. So first I take a place close to that, like let's say that's 1 and that's 2. And I draw the tangent line, and I find where it hits the x-axis. I say, okay, well that's a good guess. That's not that far away. So now I go to here, and I draw the tangent line again. Now I've got a really good guess. And I go to here, and draw the tangent line again. Oh boy, am I close. So with 3 or 4 iterations, take the answer, plugging it back in, you can get very close to the answer very quickly. So how does that work out in reality? What you do is the following. This is our formula, okay? You make a guess, which we call x sub n. Okay, we start with x sub 0, then x sub 1, x sub 2, and so on. Then to get the next guess, you're going to plug it in this formula. X sub n minus the function of x sub n divided by the derivative of x of f. The derivative at x of n. That came out badly. Let's do one in action. Okay? So say we have a curve f of x equals x squared, x cubed minus 2x minus 5. And we want to find an approximate root. We want to find about where it's 0. And we're going to start, our first guess is going to be 2. We know the answer is not 2 because we plug it in. You get 8 minus 4 minus 5 is minus 9 is negative 1. So 2 doesn't work. But 2's close. Okay, where did I come up with 2, by the way? If I plug in 1, I get 1 minus 2 minus 5 is negative 6. I plug in 2, I get 8 minus 4 minus 5 is negative 1. When I plug in 3, I get 27 minus 6 minus 5 is 16. So at 2 I was close because I had it just under the x-axis, negative 1. And at 3, I'm well over the x-axis. So somewhere between 2 and 3, closer to 2 is the right answer. That makes sense? So again, I know f at 2 is negative 1, and f at 3 was 16. Okay? So somewhere between f of 2 and f of 3 is the answer. Between 2 and 3 is the answer. All right. So let's take a guess. Now I'm going to need the derivative because this is calculus class. And now we find x sub 2. So to get x sub 2, you take x sub 1 and subtract f at x sub 1 over f prime at x sub 1. So that's 2 minus f at 2 over f prime of 2. What's f of 2? Well, negative 1. And what's f prime at 2? 10. So that comes out 2.1. 2 and 1/10. Okay. So Newton says now to get x sub 3, you do x sub 2 minus f at x sub 2 over f prime at x sub 2, which is 2.1 minus f at 2.1 over f prime of 2.1. I already know what you guys are going to ask me. Now you plug this in and you get 2.0946. We expect you to do that without a calculator. Right? No. You say, but if I can use my calculator, why don't I just use the 0 part of the thingy and just find it? The answer is, it's Newton's method, you gotta learn it. Okay? But, we're gonna have weather sign problems on this. Some of them will say, find it to 8 decimal places. Okay? So that means you're gonna keep doing this until you get 8, until basically it stops changing, which takes about 4 iterations usually. It's faster than you think. Newton's method is very accurate for these kind of equations. Okay? Or, we're going to give it to you, if we gave it to you without using a calculator, we'll make you do it, say, twice. Okay? And the first number will be easy and the second number will be easy-ish. Okay? But we might ask you to use a half. You have to be able to do things like a half squared and a half cubed. It's not that unreasonable. You are in college. Okay? But we wouldn't ask you to do crazy numbers. It's not fair. So let's try one. Let's say suppose we have something like this. Oops, sorry, too easy. No. Right, first time. Okay. We have f of x equals x cubed plus x minus 3 equals 0. And I note that f of 0 is negative 3, f of 1 is negative 3. That tells me nothing. F of 2 is 7. So there's a root somewhere between 1 and 2. You see why there's a root between 1 and 2? It's negative on the one side and it's positive on the other side. So somewhere in the middle is 0. That's the intermediate value theorem. So take the derivative. You get 3x squared plus 1. And now let's do a little bit of Newton's method. our first guess is going to be, we'll start with 1. I mean, I would guess 1.5. Okay, with a calculator, you start with 1.5, you get there very fast. Okay, but we'll start with 1 because we don't have calculators. So to get x sub 2, I'm going to take x sub 1 minus f at x1 over f prime at x1. That's equal to 1 minus f at 1 over f prime at 1. Okay? F at 1 is -3. F prime at 1 is 3 plus 1 is 4. So you get 1 3/4, or 7/4. If you have to do it by hand, don't do 1.75. Make it a fraction. Much as you love fractions, cubing 1.75 is probably harder for you than cubing 7/4. Okay, so to get x sub 3, we're going to take 7/4 and subtract f at 7/4 over f prime at 7/4. Okay, 7/4 cubed is 343 over 64 plus 7/4, which is 112 over 64. So that's 455 over 64. Minus 192 over 64 is 263 over 64. You guys can do that in your head, right? I could just be making that stuff up. You wouldn't even know. All right. 7/4 squared is 49/16 times 3, which is 147/16 plus 1/16, which is 163/16. And that's some mess. Okay? It's actually not that bad. It simplifies pretty well. But I won't bother. Okay? Then you would get this answer, and you would do it one more time. Okay? So if we give you one of these to do by hand, it won't come out very difficult, okay? Or more than 1 or 2 steps. I want you to just understand the principle. So let's have you all try one. Why not? Without a calculator, or with a calculator. I don't care. You can't use a calculator, but you can use your cell phone with a calculator app, or you could use your new Apple Watch. How many of you have an Apple Watch so far? 0. That's what I thought. Let's see. Okay? Try L'Hopital's rule twice. Feel free to use your calculators.
Corey, does this count? I want to meet up. Is this the only count class in ESS? Is this ESS?
Later, when we edit this, you'll point out that f(1) is -3. That's because I meant x cubed minus x minus 3. But whatever. We're past that problem now. So we're going to a new problem. Alright, so let's do this. x1 is 1, so we're going to need the derivative. We get 3x squared minus 1. This is a fun thing about doing the arithmetic in your head. Every once in a while you mess up. Even the guys. Okay, so to get x2, we're going to take x1. We're going to subtract f at x1 over f prime at x1. x1 is 1. F at 1, okay, we'll plug it in carefully. And you get 1, minus 1 is 0, minus 1 is -1. Now you go to f prime of 1 and you get 3, minus 1 is 2. So this comes out 3/2. Okay, so this is the type we could give you on a test. Remember, you'll have scrap paper. Okay, so to get the next guess, you'll take 3/2 minus f at 3/2 over f prime at 3/2. F at 3/2 is 27/8 minus 15/8 is 12/8. It's 3/2. Is that right? That can't be right. 27/8 minus 5/2 is 27/8. No, minus 28. 7/8. 7/8, good. F prime at 3/2 is 3 times 9/4 is 27/4. Minus 1 is 23/4. And that's something I wouldn't be afraid to ask you to do, because that becomes 3/2 minus 7/8 times 4 23rds. Go canceling. You get 3/2 minus 7 over 46. There's 124 over 92, which is 31 23rds. How'd I do? Of course, we'll let you guys arithmeticize it. 31 23rds? So either we're both wrong or we're both right. Okay. Alright, so that's Newton's method. So here's the fun part. There's only one topic left before the final. That's going to be antiderivatives. Okay? Oh. Well, how do you know when you're done? That's a good question. Well, you can keep going until you get really close. As a fraction, you start to get ridiculous fractions. So a big number over a big number. Or, as a decimal, you start, what happens is like, the fourth decimal place doesn't change. The first four decimal places don't change. Like only the fifth changes in the next one, and then maybe only the seventh. So very quickly, you've got incredibly good precision. So most of the time, 2 to 3 decimal places is really all you care about. If you want 8 decimal place accuracy, that's nice, but I don't know what you need it for. Okay? Maybe if you were designing like contact lenses, but for most things, 3 is pretty good for contact lenses. Okay? So, with Newton's method, you stop when we tell you to stop, basically. But if you do it on a calculator, you'll see very quickly that the answer won't change. It'll just keep coming out the same, which means it's like 20 decimal places out. Alright, so Wednesday, we're going to do antiderivatives, which is going backward. And now you can go study for your chem test. See you later.